Hi everyone, I hope you're okay, and I hope that the videos we keep uploading are helping you out. This is the 11th video, guys, which simply means I'm doing question 11 of the 13 promised videos, né? And each and every video, guys, will have its own questions, its own question rather, and each and every one of these questions are extracted from past exam question papers. Electrostatics, guys, is the same for grade 11 and grade 12, so it doesn't matter which grade you are in, whether grade 11 or grade 12. Just come here and work with us. You guys are doing one and the same thing, yeah. And the reason behind me answering these types of questions, guys, is that I believe that knowing how to tackle an exam question will help you whenever you write your exam. You will have an advantage because you are used to such questions. Are you together? So it's very, very important for you guys to answer all these 13 questions on your own and then compare your answers with mine. And please do share the video, guys, to your peers so that they may also have an advantage whenever they write their exam as well. Yeah, okay. Let's start working. We are told that two charged spheres R and S are both stationary on a smooth insulated surface inclined at 25 degrees to the horizontal. Sphere S of mass 0.01 kilograms carrying a charge of -6 nanocoulombs is connected to a 0.03 meter long light inextensible string attached to point P at the top of the incline. Sphere R carrying a charge of +5 nanocoulombs is held such that the distance between the centers of the spheres is R, as shown in the diagram below. We are being asked to ignore the effects of friction. Okay, we are given the diagram there. Okay, and then now we are told that sphere R exerts an electrostatic force of magnitude 1.2 times 10 to the -3 newtons on sphere S. Okay, the first question they want us to state Coulomb's law in words. It simply states that the electrostatic force between 2-point charges is directly proportional to the product of the charges and inversely proportional to the square of their distance apart. Let me repeat that. The electrostatic force between 2-point charges is directly proportional to the product of the charges and inversely proportional to the square of their distance apart. Okay, 7.2. We are being asked to calculate the distance r between the spheres. Okay. Since we are given the electrostatic force between these two spheres, I think it will be easier for us to calculate r. Because F is equals to K Q1 Q2 over R squared. Are you together? I can cross multiply over here, guys, just to make things easier for me. Né? That means R squared is basically equals to K Q1 Q2 all over F. And then R is just the square root of K Q1 Q2 over F, and therefore I can simply substitute because I'm avoiding to make mistakes. Né? That's 9 times 10 to the power 9. I have 6 times 10 to the power -9 multiplied by 5 times 10 to the power -9 as well, all over the magnitude of the force. That's 1.2 times 10 to the power -3. Therefore R is equals to, just punch your precious calculator. I have inside the square roots 9 times 10 to the power 9, and then I have 6 times 10 to the power -9. I also have 5 times 10 to the power -9, and then at the bottom I have 1.2 times 10 to the power -3, and then I'll simply get an answer of 0.015 meters. So R is basically 0.015 meters. excuse me. Okay. 7.3, they want us to draw the free body diagram for sphere S. Okay, this would be sphere S over here, né? Sphere S is held by the tension over there. This is the tension. And then since sphere S is in the universe and it has a mass of 0.01 kilograms, that means sphere S has gravitational force, Fg. Sphere S is on top of a surface, so sphere S will experience normal force as well, which is always perpendicular to the surface. And then there will be the electrostatic force between sphere R and sphere S. Are you together? So since these two charges have different polarity, one is positive and the other is negative, that means there will be a force of attraction between the two. But my main focus over here is just sphere S. Né? I want to see how is sphere S, how is this charge over here, charge S or sphere S, is going to behave as a result of sphere R. So since they're attracting one another, this charge over here, charge R, will pull charge S down the incline. So this will be the electrostatic force between the two charges. Are you together? You can draw a free body diagram like this, or draw the one, or draw the other one that has the components of gravitational force. It will be simply like this. Let me use a different color. Let me use black. Yes, I still have my tension. I still have my normal force. I still have my electrostatic force, Fe. But remember that, guys, I also have a gravitational force. Né? But instead of writing the gravitational force, I'm choosing to write the components of gravity. So I simply have Fg parallel as well as Fg perpendicular. Are you together? Please, guys, remember that Fg parallel is always equals to mg sine theta. Fg perpendicular is always equal to mg cos of theta. Always the time, né? So that's how, guys, you can draw a free body diagram. You can draw it like this or like this. But please, guys, you must fully label your forces. Do not draw it like me. Do not just write T. Please do write tension, F gravity, F electrostatics, and then here normal force. Né? Because they said they wanted a labeled free body diagram. Do not leave it like that. Okay, now they want us to find the tension on the string. Remember that, guys, we were told that these two forces, these two spheres are stationary. Are you together? So since they are not moving, it simply means F net is equals to 0. Are you together? And hence tension is just equals to the sum of both the electrostatic force and the Fg parallel. Are you together? How did I come up to that conclusion? Because whenever I'm focusing on sphere S, I'll simply say F net is equals to MA. Are you together? But how many forces do I have? I need to choose a positive direction. If I take up the incline is positive, that simply means my tension will be positive, and then the electrostatic force will be negative as well as Fg parallel. Are you together? But my acceleration is 0 since these two, since the two spheres are stationary. So that will be 0 over there, né? And hence tension is just equals to electrostatic force plus Fg parallel. Are you together? I was given the electrostatic force between charge S and R. Remember that, né? The electrostatic force, it was 1.2 times 10 to the negative 3. It was given to us over there, né? But now all we have to do is to find Fg parallel. Remember that, guys, Fg parallel, it's forever mg sine theta. Are you together? The mass is just 0.1 kilograms. that's 9,8, our gravitational acceleration, and then I have sine of 25 degrees. Let me confirm. Yeah, the angle is 25, and yes, the mass is 0.01 over there. Okay, let me just punch and find the magnitude of the tension. The magnitude of the tension, I have 1.2 times 10 to the power negative 3. 1.2 times 10 to the power negative 3 plus 0.01 multiplied by 9.8 multiplied by the sine of 25 degrees. So the tension on the string is just 0.04426. Let me say 0.043 newtons. So the tension on the string is basically 0.043 newtons. Are you together? Okay, and then now they want us to find the net electric field at point P. Okay, let me erase everything here to create room for me to write. In the meantime, guys, I hope you are subscribing over there, né? I hope you are subscribing. Since, guys, my main focus is the electrostatic at point P, the electric field rather at point P, né? Whenever I'm given a point, guys, I must always assume is a positive point charge, and its magnitude is always positive 1.6 times 10 to the power negative 19 coulombs. Are you together? Okay. For me to be able to find the net electrostatic field, I just need to know how is charge P, how is this point charge over here going to behave as a result of, charge S and the charge R over there. Okay. Remember there we got 0.015 meters, if I remember properly. Okay, let's draw a free body diagram, guys, né? This will be charge P, and that's our incline over there, né? This is charge P. Let's see how is charge P going to behave as a result of charge S. Are you together? Since both of them have different polarity, this is negative and that's positive. That means there will be an attraction force between the two charges, and hence our sphere S or charge S will try to pull the point charge down the incline because they are attracting one another. Are you together? This is the electrostatic force due to charge S. Are you together? The electrostatic force between the point and charge S. Okay, now on a blue color, let's see how is the same point going to behave as a result of charge R. Charge R is a positive charge. Are you together? So these two charges are both positive. So basically they're just pushing one another away. But my main focus is on the point charge, which is at position P. Are you together? So since charge R pushes the point charge away, so charge R will push it up the incline like this. So this will be the electrostatic force between sphere R and the point charge. Are you together? So remember that, guys, the electrostatic force is always in the direction of the electric field. So if the electrostatic force due to charge R and the point is up the incline, that means the electric field due to charge R rather is also up the incline. Are you together? If the electrostatic force due to charge S forces the point charge to go down the incline, so does the electric field. Electrostatic force and electric field are always in the same direction. together. So for me to find my inlet, all I have to do is to just choose rather a positive direction. Since I know that the electric field due to charge S would be greater than the electric field due to charge R, I know that because the distance is smaller, I will choose down the incline as positive. Down the incline is positive. That means up the incline will be negative. So for me to find my inlet, I'll simply say inlet is just equals to the electric field due to charge S minus the electric field due to charge R. And then all I have to do now is to just substitute that K, that's K QS over R squared minus K QR over R squared. K is given to us, that's 9 times 10 to the power 9. The charge on sphere S is 6 nanocoulombs, ne? Yeah, that's 6 times 10 to the power negative 9 all over. The distance between sphere S and the point charge at P, that's 0.3 meters, 0.03 squared, ne? Minus 9 times 10 to the power 9 multiplied by 5 times 10 to the power negative 9. The distance between R and P is 0.03 plus 0.015. 0.03 plus 0.015. We'll simply get 0.045 all squared. And then all I have to do now is to punch my precious calculator to write down the net electric field and its direction. That's 9 times 10 to the power 9 multiplied by 6 times 10 to the power negative 9 all over 0.03 squared minus 9 times 10 to the power 9 multiplied by 5 times 10 multiplied by 5 times 10 to the power negative 9 all over 0.045 squared. So I'll simply get an answer of 37,777.78 rather newtons per coulomb, and the direction is just down the incline. So that's how, guys, we're supposed to deal with that question over there. I really hope that the video helped you out. Thank you for your time.